Yes, sir. So this diagram doesn't have the annulments. Well, I'll start putting them in again. So there's a difference between annulments and stalls, right? An annulment means is when we actually throw away an instruction. We replace an instruction that would have been executed with a no-op. So that's what happens when we do take a branch. We actually throw away the instruction following the branch. A stall, we actually will execute the instruction at some point. We just can't finish executing it now. So they're really different. And so there's two ways no-ops get into the pipeline. One is when I'm replacing an instruction. One is when I'm filling in an empty spot in the pipeline, but I'm actually not replacing any instructions in the program. So no-op is not a sign of annulment everywhere. It sometimes is a sign of, I got to tell you to do something while we're waiting for the right thing to happen. Okay, so we wanted a clean, simple pipeline, so we had the ability to do a no-op here. And remember, the no-op in this stage was actually an annulment no-op, the replacing of an instruction we did not want to execute. We inserted a whole bunch of bypass paths. I love this sort of heart shape. So think heart when you think bypass. And you can see that what we're doing is taking the values from downstream pipeline stages, instructions that came ahead of us in the program and are ahead of us in the pipeline, and grabbing their values before they actually get written into the register file. Okay, and then we had to add the ability to freeze the top half and insert no-ops while an instruction was stuck in the RS stage while the load made its way all the way down to the right back stage so we could grab its value. So this particular no-op, at least at this stage in the lecture, is really there so that I can wait for loads to, for the memories to complete and for me to actually have the value that I need to get for any instruction that uses the result of the load. Just to make really crystal clear the picture of where the bypasses go and everything else, the bypasses actually go sort of right next to the register file. All of our logic that operates on the contents of a register, where we, taking the jump address or testing to see if a register is 0, or feeding the value into the A cell mux or the B cell mux to select between a different number in the register contents. All of these things operate on, quote, the value of the register. This mux is selecting the correct register value, either from the register file or from downstream pipeline stages. And so this wire coming out of the bypass mux is, quote, the correct register contents. Everybody got me on that? So we've just sort of randomly been drawing, multiplexers in the RF stage, and now on this slide I'm very careful about showing you exactly where that goes. Okay, so we've been a little sloppy about that, and we've cleaned that up. You might say, oh my God, this is a 17 input 32-bit mux, isn't that sort of big? Well, if this was a VLSI class, I could show you some pictures showing you how to implement that very, very compactly. And in fact, you can do some neat tricks with tri-state drivers to build a mux, and you can do the layout of your system in such a way that it turns out this is not a very expensive thing to do, even though it looks horribly expensive the way we've been drawing it. 32-bit buses going everywhere. It's not as bad as it seems. So, okay, a couple other things to think about. This very strange program, which I don't recommend for anything in particular, except to sort of show you that in fact we have this situation that that we need to figure out. Here's the branch register writing something in the LP register, and I'm branching to a location that's going to use the LP register. And what we're pointing out is that not all of the information that we want is in that middle vertical column of our processor diagram. The point of this particular strange program is to sort of observe that occasionally the contents of the register don't come from the ALU or from the memory. Where else can the register contents come from? There's one other input to the WD cell mux. We write PC plus 4 into the register file when we do, for instance, when we do a branch, a taken branch. Okay, so when that happens, what we need to do is sort of observe that we need to not only bypass from all of this stuff over here, we need to also include bypasses from the other things that can go in the register file, in this case the PC+4 value, which is dutifully also flowing down the pipeline. So it turns out that our bypass muxes are even piggier than you thought. Not only are they bypassing 32-bit values from this wire or down here, but we also occasionally have to be able to bypass them from the PC+4 values in the ALU or MEM stages.